So again, thank you for joining us again today. We are going to discuss Module 3 of our virtual power monitoring series. And Module 3 is going to focus on power quality monitoring. We're going to talk about an overview of power quality monitoring, some of the latest on standards. We'll also give you some case studies on power quality as well. So let's get started here. And the first thing is to kind of define what really is a power quality problem. A lot of textbooks don't really define that. So really a PQ problem is really, do these wave shapes that can occur regularly, do they affect your systems? Do they represent a problem for you? So as an example, this is a voltage dip or a sag. This is a noise on your waveform or a transient. This happens to be induced by a power factor correction capacitor switching in. This is a transient. These are harmonics. This is a swell. And this is kind of a long-term reduction in voltage, okay? Really, it's not that these problems occurred, but do they affect your systems? That's the most important thing to understand. So our meters will capture this, but do you have susceptibility? So really, it's a PQ problem only if they cause your equipment to misoperate or fail. All right, that's the important thing. And it's not only are they failing today, but do they have susceptibility to these types of issues where maybe they're not failing today, but maybe it could be a future problem if things line up or maybe something gets slightly worse. So again, what does it mean? It depends upon your susceptibility. So given the quality of supply, maybe these pictures over here, these things are happening. Do you have to be concerned about problems with your equipment or your systems? Are you susceptible to that? That's extremely important. Even more important is not only your susceptibility, but what's your economic exposure to that. So let's say you do have susceptibility to these problems, but really, practically speaking, is it going to be an economic problem for you? Either a huge convenience, out-of-pocket cost, downtime costs, things like that are very important to understand and know. So each time I have an event, it's what's the downtime, how much does it cost versus what it costs me to mitigate these problems and prevent them from happening. Beefing up your power systems, installing generators, UPSs, whatever it takes in your particular application. What's the investment it costs to do that, to mitigate it, and what's the payback versus the downtime? If it's going to be a payback in a couple months, well, that's usually okay with the accountants and management to go invest some money. If I will not get payback, if it doesn't cost me or your company that much when a problem occurs, well, maybe it's not worth mitigating that problem. You can't get budget to go do that. So these are kind of introspective sort of conversations you need to have within your own organizations on susceptibility, but also the economic exposure to things. A lot of people need to get rid of these problems and mitigate them, usually for mission critical and other critical applications. So, power monitoring comes along with this. And what are the benefits of power monitoring? The first one is problem avoidance and prevention. So case studies have shown that being a little proactive on your power monitoring can increase reliability by detecting issues that really may not have turned out to be a major issue yet, but it's kind of looming on the edge of being a problem. So we've seen a lot of issues with our customers where they see issues and they know that their systems can potentially have susceptibility. So they proactively correct or mitigate these issues before it turns out to be a large outage or an interruption or downtime, whatever is critical to that facility. Now, again, on a proactive basis, understand your facility. If you don't monitor it, you can't measure it. So you need to understand what's going on. Certainly, if you have a critical operation that's highly reliant on power and the quality of supply, not only how much you're consuming, but when you're consuming it, power monitoring comes in to help you identify the quality of supply, how much you're using at each point, and to see whether those things kind of overlap and are going to create an issue for you. And then on a reactive thing, well, should problems occur, if you're monitoring, basically you can go back and you can look and find out what the source is. So power monitoring, specifically power quality monitoring, is kind of like a DVR for your facility, putting it in modern terms. So should someone report a problem and say, hey, something went down at a particular time, you can just go back in time for your PQ data and say, well, do I have an issue at that particular point in time? What's my voltage? What's my current? Maybe harmonics and other things you may have susceptibility to, and say, did anything happen at that time? So you can reduce your troubleshooting and your downtime, but saying, hey, yes, we had a PQ problem at this time. It looks like this is what's going on. This is what we need to correct the problem in the short term and maybe the long term to mitigate that. Or on the other case, no, there wasn't a power problem. Maybe some servers locked up, or there was a hardware failure in whatever system that went down, whether it be a computer system, a manufacturing a line or something like that. So, power monitoring will help you identify that a power problem occurred and maybe what the source of that problem was, or to rule out power as a source of the problem. And then you can continue on and look at other systems, maybe the computers or the manufacturing line. And the big thing is it prevents the finger pointing. And a lot of times in our industry, something locks up or dies, it's a power problem. And it may be a power problem, but of course, it's not always the case. And you need that information to kind of proceed and rule that in or out. So just as an introduction to power quality, we're going to talk about, well, what are the general sources of power problems? And we're going to, in our example here, hypothetically, we're going to reference the point of common coupling, the PCC with utility. And we always do that because that's a nice place to reference, because upstream from that point, it's the utility's responsibility. Downstream from that point, it's internal to the facility. So it's the owner of the facility's responsibility to deal with and mitigate those issues. So when we talk about issues on the utility side, we of course have weather and other things like lightning and other things that can affect the quality of supply. Those power factor correction capacitors, and I showed you a little blip about that before. We'll talk about that in a few minutes. Fault switching, impact from other customers can affect your power quality. We have case studies with nearby customers introducing sags and dips, also harmonics on the power line nearby that's basically being conducted into your facility. Well, internal to the facility, we have individual loads, motors, adjustable speed drives. I just got off the Zoom this morning with a customer in Texas who's got concerns about adjustable speed drives and their susceptibility to some power issues that they're having. So anything that's computer-based, microprocessor-based, whether it be just computers or PLCs or anything controlled, well, they can have susceptibility to power quality issues. Wiring problems, changing loads. So really a lot of stuff can happen. But again, knowing where it happens is extremely important, looking at the point of common coupling. Upstream from that point is the utility's responsibility, typically. Downstream is your own responsibility or whoever owns the facility. So we're going to do a quick poll here, and really who is responsible for the power problems. So let me just start this poll. So hopefully you guys can see that now. So really, who's responsible for most power quality problems? Is it the utility or is it the end user? So let's give it a few seconds. I see you guys voting here. Got 36 votes, 38, 41. All of you got to vote. It's not a democracy here. You don't have that choice. So we've got about 54. I think everyone's voted, 55 now. All right, let's end the poll here. And so we've got 9 of you said it was the utility, and 46 of you said it was the end user. So let's share the results here so you guys can see it. Hopefully you guys can see the results there. And then we'll go back to our slide. And hang on, I think I have to change the sharing here to make sure we're on that, which we are. Ken, can you see that? Okay, I'm sorry. I got to shut down the poll here. Hang on. How about now? Okay, hang on. We're stuck on our poll here. Just bear with me. Close that out. How about now? Okay, I'm sorry. All right, let's stop share. Let's resharing. I apologize for this. Sometimes we get a little hiccup in Zoom here. How about now? Okay, okay. Sorry about that, everyone. Okay, but the slide, the PowerPoint, right? Okay, we're good. So here's the answer over here. Who's responsible for most PQ problems? Well, typically it's the end user. So about 70% statistically of all PQ events are generated within the facility itself. So really what that means is that, of course, there can be issues on the utility system. 25, 30% of the time, according to the statistics that we had. I think a lot of those originated from EPRI at the time. However, end users most likely are the source of their own problems. So utilities work with end users in varying capacities once they understand where the source of the problem is. But this is something that either you, as an end user, you have to resolve yourself, or sometimes your utility will give you assistance in resolving problems that are originating within your facility. So let's talk about the power monitoring terms and what are the references and things that we talk about here. Well, there's some standards that we're going to talk about. And in the United States, we have recommended practices. Very rarely from the power monitoring side do we have absolute requirements. Some of the things for harmonics and other things may be loaded into some of the utility contracts that you have. But generally speaking, we're talking about recommended practices. And the two most common that we refer to in the United States with the IEEE are the first two here. IEEE 1159, which covers a lot of the terms that we talked about here. What's a sag, what's a swell, what's a transient. And also IEEE 519, which has just been recently updated about 6-7 years ago. And 519 2014 talks about harmonics, what a harmonic is, and also statistical compliance information about harmonics for voltage and current. And we're going to focus on this at our next webinar. I think it's on June 1st, where we talk about harmonics. And so what they've actually done is they've harmonized with some of the international standards on harmonics. So when we switch gears, the IEC, this is really who's leading the way and has led the way on the power quality standards and the definition of them. And the IEC kind of covers Europe and Asia and other places like that, with a focus on Europe. And they came out with a standard somewhere around 2003 called IEC 61000-4-30. Its current edition is edition 3, which is from around 2014. Now they're working on the next revision to this standard. But really what this defines, it basically tells PQ meter manufacturers such as Transients how to build a power quality monitor. We're not talking about chips or what it's going to look at, but it gives us the math, the algorithms, and some specifications to acquire voltage, to acquire current, harmonics, flicker, and other things that are included in these standards. Okay. And again, it's in its third edition right now. And really, there's several classes to this standard. And if you're Class A compliant, you have full compliance with the standard, and it means you'll have repeatability of measurement. There's an issue in the or has been an issue in the power quality monitoring business where you put 2 meters side by side measuring the same thing from different manufacturers and you may get different answers. And this is meant to correct that issue, that if you're compliant with the standard, both of the meters from different manufacturers or even within the same manufacturer, they complied to the same measurement techniques, okay? And that's important where they defined. Okay. Also, you have in Europe, you have some other things, specifically EN 5160, which has evolved over the years, which is a quality of supply standard. And it's more of a utility reference. And really what it means, simply put, and at a high level, that your limits are within, you're within limits 95% of the time is what I should say better. So really, why should you care about power quality measurement standards? And the first one is you may be required to, just based upon your geography, where in the world you're doing your measurements or you're located. So 61000-4-30 is required in parts of the world, specifically Europe. Other parts in Asia and other countries do either require it or reference it in their own versions of standards. So you may be required, and sometimes if you're going to present data to a utility, legally, you have to comply with the standard for them to accept that data as being valid. But if you're not in that part of the world, like in the United States or in other parts, well, it gives you the reliability of the measurements. And some of the benefits are, which we talked about before, again, our industry challenge of consistency and repeatability of measurements. And Transients, and specifically the PX5 family, was the first product family back in about 2004, 2005 to actually comply with the 61000-4-30 because of this, its consistency and repeatability of measurements. So if you have a compliant meter, you can trust the data, you can have confidence that the instrumentation can appropriately detect and report the issues that you're asking it to do, and that data can be trusted. Now, you may think, is sitting here in the United States or other parts of the world that don't require this standard, these measurement methods are applicable in the US and other parts without compromise. They don't take away. In fact, as I mentioned before, the IEEE and other standards bodies have adopted or harmonized with these IEC standards. So they may use them exactly or maybe add to them. So they're used without compromise. Now, several years ago, 2015, 2016, another standard was developed, IEC 62586, and basically that's a testing standard to this 61000-4-30. So really it defines the test methods to make sure an instrument complies with that. So it gives the opportunity where a manufacturer or a laboratory can provide a compliance certificate to 61000-4-30. And we'll see a picture of that on our next slide here. So the bottom line is most reputable PQ or meter or instrument manufacturers offer some compliance with the IEC method. So it's up to you as a consumer to understand, well, what do they comply with? Is it Class A? And do they fully comply? But also maybe, do they test for compliance, and can they prove it in any way? So that's important, because certainly in parts of the world that may be required based upon legalities and things, but otherwise as a consumer, it gives you the confidence that you're buying from a reputable manufacturer. And just realize that most entry level meters do not or may not comply. You do get what you pay for. I'm not, don't mean to imply they're not good, but they may not have the same measurement techniques as some more advanced meters have. And these days, the cost of the meters will come down significantly to get this Class A compliance. Well, last but not least here, IEC methods are now being called out in the United States. And the IEEE is harmonized with some of these related standards, specifically for voltage flicker, and more recently, the IEEE 519/2014, which took the IEC methods to measure harmonics and harmonized them and adopted them exactly. But the IEEE added statistical compliance on top of that. So they use the same measurement techniques, but they had compliance statistics for voltage and current, THD, TDD, and harmonics and stuff that are added to that. Again, we will focus on that at our next webinar on June 1st, where we'll talk about harmonics. Another reason is some of the compliance standards are starting to call these out for the measurement of power quality. One example is IEEE 1547, which is intended for DERs, or distributed energy resources, and that is starting to reference the harmonic and power quality measurements included in modern PV, wind, or whatever DER system. So it's what this is basically saying. They're starting to not only look at the safety and production of energy from PV and DER systems, but also how well they're working with the utility. And are they being, friendly to the utility? Are they introducing problems? Are they cooperating and not affecting in a negative way the utility systems? So, and that goes to reliable PQ monitoring specifically to these standards. Excuse me. So what you see here, this is a compliance certificate. This happens to be for our HDPQ product line. You see HDPQ Plus here. And what you see here is that the test methods used were this IEC 62586, which is the standard that I talked about, which is testing to edition 3 of IEC 61000-4-30. That's what's circled here. And there's many more pages. This happens to be the cover letter, or the declaration of conformity, the compliance certificate for these standards. And that's backed up with kind of pass-fail of every major portion of this 62586, which tests for flicker, harmonics, and other aspects of the 61000-4-30 standard. And you can see here's another example of more of an IEEE 1547 application. And this is kind of a depiction of a fairly modern utility grid. Well, in the past, I mean, forget about the wind, forget about the solar, power was generated and got kind of rippled down to the consumer, whether it be an industrial consumer or a residential consumer. But the point is, they were really only concerned about consumption. Okay, how much power flows through the system? Well, with the advent of DERs, again, distributed energy resources, well, you have power production either owned by the utility or owned by third parties that can be injected in different locations, from the even the high voltage system to the medium voltage system down to the low voltage system as you get closer to the consumers of electricity. So meters that used to just be bidirectional, or even just one direction energy meters, or unidirectional energy meters, which is just measuring the flow, now actually need to be bidirectional energy meters to not only determine, well, how much is being introduced and consumed at different parts of the system, but with also quality of supply capabilities to them, meaning that at these points, if this is a privately owned DER system, well, is it behaving well and properly interfacing to the utility system? Is it injecting harmonics? What's happening on a cloudy day on a solar system, when it doesn't really produce much? What's it doing and what's the interaction here? So it's basically looking and saying, well, how is it behaving and are there any PQ issues going along with that? So the point here is that things were just energy meters years ago, in a lot of cases are now energy meters, of course, because the whole point here is for energy production, but also with power quality capabilities to make sure that these DER systems are behaving well and interfacing appropriately in the system. So now, last but not least in this section, just a brief update. I mentioned before IEC 61000-4-30. Its current released edition is edition 3. However, edition 4 is in the works right now. It's moving towards a release. It's in its draft stage right now. It has been distributed to each country for comment on the release of edition 4. So maybe sometime later this year, it will be released, I guess, depending upon what those comments are. In fact, there's a US committee meeting on Friday, which I'll be attending in regards to that. So the significant changes, really the base measurements are really the same. There's not much of a change in that. The most noteworthy is rapid voltage change measurements, which are more important in Europe and other parts of the world than the United States. And these are basically small changes in drifting in the voltage within the limits. So you have a high and a low limit. This is kind of drifting within those. And there's an improvement and some new measurement methods for that, that us as meter manufacturers will have to adopt to or adapt to. But really the most noteworthy thing are new annexes, or in the informative section of the standard as of now, on superharmonics. And what superharmonics are harmonics or frequencies in the range between 2 kilohertz and 150 kilohertz. And we're going to cover this. We'll provide a focus on this in our next webinar on harmonics, but this is something kind of new to power monitoring. And this is more actually spectrum analysis on the power lines to see what the effects are. So again, these are the two most significant changes, and we'll discuss the superharmonics in our next module. There's a lot of interest in this. As an example, recently I've done some conference presentations and I've touched on superharmonics. It generates a lot of conversation and questions related to that. So let's start breaking things down and start defining some of the power quality issues that we have. And really, we're going to focus on the first 3 here in the examples. Actually, I'm sorry, the first 2 here that we're going to focus on. The harmonics are going to be a separate webinar next or in about 2 or 3 weeks. But we have transients and RMS variations that we're going to discuss today. So we're going to break those down. So completing it, there's also harmonics, which again will be our next webinar. There's also flicker, which is voltage fluctuations, frequency variations, main signaling, other power quality issues. But these are really the most common, and specifically the first 3 here are really the ones that are referenced and considered in most PQ problems and problem solving. Although, again, there are more defined by the standards and, of course, that the meters are capable of recording. So we're going to do another poll here. Hopefully we'll be able to get in and out of this poll a little bit more easily than we did before. And let's see if this comes up right here. So we shared the results of this one. I want to stop sharing, and it's not letting me go to let me choose the next poll. And so let's launch this. So you can see the question is, which of these PQ problems occurs most frequently? So please cast your vote here. We'll give it a couple seconds here. Is it a transient, which is a very fast change in the voltage? Is it a voltage swell, which is a increase in voltage? Is it a voltage sag or dip, which is a decrease in voltage? Or is it an interruption? No voltage exists there. So which of these occurs the most frequently statistically? So we'll just give it a couple seconds here. We've got about 50, 52, 53 who have casted their vote. And I think we're just about done here. So we're up to 54. We're going to end the poll, and we're going to share the results. And you can see here, people thought, and correctly so, that sags and dips, an undervoltage, a temporary reduction in voltage, statistically occurs about 2/3 of the time, much more frequently than the transients, the swells, or the interruptions. So really, so what we're looking at most frequently, it's basically voltage sags or dips that occur. So let's see, we share the results. Let's see if I can close this. And Ken, did we get back to our main slide here? Okay, so we're back to the main slide. Thank you very much. Okay, and you can see here which of these problems occurs most frequently. It is the voltage sags of the dip. So it's in kind of a temporary undervoltage situation. These issues do occur, the transients, the swells, and the interruptions. But again, statistically, this is what we're watching out for. Quite to put it crudely, this is why UPS systems and voltage support gets added to a lot of the systems to mitigate some of the power problems that we find. So let's start breaking these down and defining them. So what is a transient? Well, it's a momentary and of course undesirable high frequency subcycle event. It's much easier if we put pictures on them here. So just to set this up, this is not a real event stream captured by a meter. This is kind of taking some artistic renderings here just to show you the different types of transients that can occur. But you can see they're all subcycle. By cycle, we mean one AC cycle, 60 hertz here in the United States and North America, and also 50 hertz in Europe and Asia and other parts of the world here. So you can see there's different types of events or transients that occur. You can see this is a positive transient. This is a positive unipolar transient, which means it only goes in one direction. This happened to go up and then down. Now, what a positive transient means, it does not mean that it's on the positive part of the waveform, means that it's adding energy to the wave shape. So this is a positive transient, an overvoltage situation, very short term. But you can see this is also a positive transient. It just happens to be occurring in the negative half of the wave shape. Okay, you can see here is a negative transient, and it's kind of the opposite of a positive transient. It subtracts or it takes away energy from the waveform. So here's a negative transient. It just so happens to be occurring in the positive part of the wave shape here. So again, as I mentioned, you have the unipolar transient. Okay, it goes up and down or down and up. It only goes one way. A bipolar transient, well, it can oscillate and go up and down, multiple times. So as an example, a power factor correction capacitor switching in, and this may be an example of it here, is a negative going bipolar oscillatory transient. And you'll see a better picture of it a little bit later, but it means it starts as a negative transient. It oscillates for a while, which means it's bipolar, goes up and down. And that oscillation is basically the damping or switching in as that power factor correction capacitor settles into the system. So typically you'll see a signature negative going transient that oscillates after that. And that's what this is a picture of. So you also have notching. You can see this maybe is from a pulse rectifier where it's just carving out sections of the wave shape. Now this creates not only transient activity, but you can also notice harmonic activity from that. Again, we'll focus on the harmonics in the next webinar on harmonics. And again, another picture of an oscillatory transient here. So here's a unique transient here. This is a negative transient that can also create frequency counting issues, which is very unique. There's still circuitry out there that's such as just low-end digital clocks that counts frequency by looking at zero crossings. So as an example, we have one zero crossing going from negative to positive, a second one here, a third one here. Well, this transient and this transient and these transients over here are creating additional zero crossings. So basic circuitry that's counting zero crossings to just get crude frequency measurements, basically it will be tricked by a transient here. So it's just something that you have to keep an eye on. Our instrumentation goes to great lengths to not to be susceptible by stuff like this when it is measuring frequency. But of course, these are power quality issues that need to be reported by a capable power quality meter. So transients, what are the possible causes and effects of transients? Well, again, we talked about that power factor correction capacitor energizing. That's very, very important here. That's a very common one. In fact, right down the road here, the utility system, 5:30 in the morning, we see one virtually every day. Lightning, that's a very, very large concern when we talk about transients, certainly a positive transient. So again, a positive transient may blow something up, a negative transient may lock something up, may be the kind of the cause and effect. So again, loose connections, load sources switching in or out, RF bursts, they're actually known to be induced into power systems. Well, what are the possible effects? Well, a lot of things can happen. Data corruption, so communication systems can be interrupted. Equipment damage, and I mentioned blowing things up and locking things up, depending upon if it's a positive or a negative transient. Related to the data corruption or data transmission errors. Intermittent equipment operations, so transients can be like ghosts. They occur, they stop occurring. It depends upon what's going in on the system, especially when we have loose connections and things like that because it's completely random. So you can have intermittent problems as a result of that. And certainly repeated transients, mostly positive transients, can reduce the life of electronic components, power supplies, and things that are exposed to that. So you can kind of consider, we'll go back a slide, if a lot of positive transients are occurring, well, maybe it can weaken the front end or the power supply of these electronic components of whatever's there, whether it be for your circuitry, for your switch gear, or also the loads that are plugged in, the servers, the switches, and things like that. It can kind of reduce the life of electronic components and specifically their power supplies. So switching along to RMS variations, these are things that are a little bit longer, and typically we consider them maybe a half a cycle and longer. So really, what is an RMS event or variation? It's a change in the RMS voltage. So really, as a fundamental math tool, the meters are measuring the RMS. We're not measuring the peak, we're measuring the RMS of each waveform. In fact, it's we step not waveform to waveform, but we advance 1/2 cycle based upon the international standards. But we're always looking at one AC waveform, whether it's on 50 hertz or 60 hertz, measuring the RMS and kind of looking at high-low limits based upon that. And those are based upon your settings. So we're looking at a change in the RMS voltage, typically that's beyond 10% of nominal. And that's what the IEEE, specifically 1159, recommends. But this can really be any limit, and this limit depends upon the susceptibility of your power systems and maybe what type of mitigation equipment you're using. And we'll touch on that in a couple slides here. So we're talking about some new terms here. Reduction in voltage is a sag or interruption. We'll see a picture of this on the next slide. And an increase in voltage is a swell, okay? And a temporary increase. But again, a picture's worth 1,000 words here. And again, what the metering's doing, it's measuring the RMS of every cycle. Don't be tricked by these horizontal lines. They're just meant to be kind of limit references here, not looking at the peak of anything. So when we look at the RMS of each, you can see we have 3 cycles of normal behavior here. We have a 3-cycle sag or a dip in some of the European international terms, a 3-cycle swell or increase over the limits, and this is a 3-cycle interruption that occurred. And an interruption means really voltage is no longer there. All right. Now, edition 3 of 61000-4-30 actually requires us, and Dranitz has done this for 20 years or more, to measure current as well as voltage, and it's measured in the same way. However, you do not use these terms sag, swell, and interruption typically. Although people reference it, the standards do not cause a reduction in current. They sag and an increase in current as well. It's just kind of high-low limits. But for voltage, sag/dip, swell, and interruption, and you can see a picture here. Okay. And again, remember that we're not measuring peaks, although our meters do measure that. But for the sake of high-low limits and triggering, we're looking at the RMS of each wave shape that comes through the meter. So what's the definition of a sag, a swell, and an interruption? So really the IEEE 1159 as defined here, basically we're looking at 2 things. And we mentioned that we're looking at the magnitude of what's happening. So a sag is defined as between 10% of 90% of what it should be. So in a hypothetical example, if I'm just looking here in the US, if I measure the outlet on the wall over here, it's looking at a 120 volt nominal system. So 90% of that, or 0.9 PU, okay, would be 120 volts minus 12 volts, which would be 108. So really what that means, if I cross below 90%, which is 108 volts, that's going to start a sag. And a sag category goes all the way down to 10% of that nominal. So it goes down to 12 volts. So a sag is defined when the voltage goes down below 108 volts and above 12 volts, that's considered a sag, okay? A swell is basically the opposite of a sag. So when it goes beyond 110 volt, 110% of nominal. So in this hypothetical example of a 120 volt system, when it goes beyond 132 volts, which is 120 volts plus 10%. So we talk about an interruption, though that's less than 10% of nominal. In the US, I think it's 5% of nominal as far as what the IEC considers that. So again, we go down to 5 or 10% of nominal, then it's called an interruption. So now we've got the magnitude of high-low stuff going on. Well, the IEEE says, well, how long is this occurring? So there's 4 time categories. And basically, the way the metering works based upon these requirements, when one of these trigger conditions is met, a sag, a swell, and interruption, we kind of set a timer in the meter. Goes to how long it occurred. So an instantaneous time category is anywhere from half a cycle to 30 cycles. Momentary picks up where instantaneous leaves off. So that's any time period between 30 cycles and 3 seconds. Then we go into temporary, which is 3 seconds to 1 minute. And then something called long duration, which is beyond 1 minute. We don't know when the voltage is going to come back. So like as a hypothetical example, if we have a reduction in voltage down to 50% of nominal for 10 cycles, that would be called an instantaneous sag. And when you go to a Transients meter, you'll see that on the screen itself. Also within the DranView software, it'll say you'll have a sag, and it's called an instantaneous sag. And certain meters will also give you the directivity of that sag, which we'll cover in a couple slides here. All right. So that's basically what the meter is doing. It's looking for the magnitude, and it's doing high-low limits based upon that and measuring how long it's gone out of limits. Now, one point of note here is on a 3-phase system, this timer, this time counter starts when the first phase goes out of the limits. And these are, the plus or minus 10% or whatever you set the meter to. And it ends when the last phase returns to normal. So let's say I have a 3-phase system, and phase A goes out of limits first, but phase C comes back within limits last. It's that time difference. So if phase A hypothetically started the event, phase C ended the event, that's the overall duration of the event. And that's what's used to look up to see whether it's instantaneous, momentary, temporary, or long duration. Okay, so I've got a monitor. How do I set up my instrument? Of course, we're focusing on Transients products here. So how do you know if you have a problem? And so there's a couple things to consider. The most important thing here is to use your equipment or your system specifications, if they are available, to set these higher low limits. The Transients products, certainly the HDPQ family, excuse me, will default to plus or minus 10% of what the nominal is. So again, in our 120 volt example, plus 10% will be 132 volts. That would be the high limit. Minus 10% will be 108 volts. And the same goes if you're 277, 480, and it'll ripple through accordingly. And again, those are the recommended practices, hint, recommended practices and limits from the IEEE. However, you may have equipment specs that maybe are susceptible in a tighter or maybe even looser voltage range than that. So as an example, if I connect my HDPQ to the output of a UPS system, and my UPS system is regulated to plus or minus 5% of nominal, as a kind of a hypothetical example, it doesn't make sense to set my meter to 10%, because at 5%, if my output of my UPS exceeds that, my UPS is out of tolerance. So what we recommend is take the weakest link or the tightest specification in your system, in this case, plus or minus 5%, use that as the limits for the meter. So the limits of your meter are tied to either the susceptibility of your equipment, if you're looking at specs on your equipment, or the tolerance of your mitigation equipment, in this case, the UPS system, if that makes sense. Okay. So you just simply enter that as the high or low limit on the HDPQ, either as a percentage or as an actual voltage, depending upon what you prefer. And again, if you don't know how to do that, we've got tutorials up on the Transients website under the support tab, and the last item, which is webcasts, and we have some demonstrations on how to set up the HDPQ for this and many other applications. So let's switch gears here and let's talk about sag directivity. And we're going to go switch to DranView here, and hopefully Zoom will cooperate. Let's stop sharing here real quick. Let's share my DranView screen. And hopefully you folks see that. We good, Ken? Yeah. Okay. So, in our CAN seminars, we have this, kind of, in a PowerPoint presentation, but let's show you a live definition of what an upstream and a downstream sag is. So what I mentioned before, the important things are, when you have a a voltage problem or a PQ problem is where did it come from? We talked about the looking at the utility service entrance, but really the rules that I'm going to tell you here for sag directivity apply no matter where you're measuring, okay? Whether it be at the terminals of a load or at the utility supply. The utility supply just defines responsibility here. So just for the sake of argument, let's say I'm monitoring or measuring at the point of common coupling with my utility, all right? There's kind of two things that happen. I can have a sag that occurs upstream from that monitoring point or a sag that occurs downstream from that monitoring point. So how do I understand the difference between them? Really, the way to look at that is you look at the relationship between voltage and current. So if you see here, the first event that I have highlighted here, you can see the voltage goes down and the current goes up. So maybe this is a motor or some sort of load turning on. So you can see this is a downstream sag. Voltage goes down, current goes up. That means something turned on. Usually that's load-based that caused this, all right? You can see here's the data within DranView. It was categorized as a short duration instantaneous sag, and its direction was downstream. So when you have the HDPQ products or even their predecessors, the entry-level Visa product does not have the sag directivity answer module. So what that means, you need to interpret this data yourself and play back this webinar and know that when the voltage goes down, the current goes up, that is a downstream event. If you own the HDPQ guide, the HDPQ Explorer, or Explorer 400, it has what's called a sag directivity answer module. Basically, it's a geek in the box that interprets this information for you and puts in the database, which you would also see on the instrument, its directivity assessment. So what it's saying, this is saying a short duration instantaneous sag, which you'll get with all the meters, but the guide and Explorer meters will tell you it's downstream in this case. It'll do this analysis for you. So an upstream sag is the opposite case, where if the voltage and the current goes down simultaneously, and you can see here's the voltage, you can see it goes down, here's the current, you can see it goes down. Well, this is another short duration instantaneous sag, but this is upstream. So this HDPQ guide or Explorer identified that properly as upstream. So again, as a review, the voltage and current go in opposite directions, specifically for a load-based something turning on, the voltage goes down, the current go up. That's a downstream directivity for that event. If the voltage and current go down at the same time, it's an upstream. Consider no voltage, no current, right? You can't draw current on a supply that's being temporarily disconnected or has an issue. Okay, so that's the difference in directivity and an upstream and a downstream event. So let's go back to our PowerPoint slide here. And hopefully that's shared properly, and we'll just skip through those because we just did those live. So what's the voltage variation, sags and swells, and what are the causes and effects? So as you can tell by the directivity, what's a possible cause? Sudden change in load current. Obviously, something's turning on, something's turning off. That can be very important to this type of application here. So a fault on a feeder, fault in the utility system. So a fault on a power feeder. So really anything can cause any problem, any disturbance. In fact, a lot of them that cause transients, loose connections, loose wires, they can also cause sags and swells. So what are the possible effects? Very similar to transients: process interruption, data loss, data transmission errors, computer lockups from PLCs, they can misoperate, and damage products, if you have big extremes. So really, again, statistically, we said before that it's the sags and the dips that occur statistically most often. So that's why you need to pay a little bit more attention to them. Okay, last but not least here, we're going to share a case study, and it's going to tie some of this stuff together. This is a real world case study, and I'm going to share DranView again. And I'm going to change tabs. I already have it loaded here. And we're going to talk about a generator testing application. And you can see a whole bunch of variations here, and it kind of ties together some of the terms and certainly the analytical techniques that we used before. Now, just to set this up, this is a real world commissioning test at a data center somewhere on the West Coast. I can't disclose anymore. And typically when our users or technicians or owners or their service people are commissioning or testing data centers or mission critical or high reliability centers, they basically usually have UPS systems, backup generators, and of course the utility supply. So what they're doing is they provide these what's called impulse or transient tests. And really by transient, it means a change, not the high frequency transients that we're talking about here for power quality. But what they'll basically do is step the load through load banks usually to 25%, 50%, 70% to 100% of the current capacity on all three phases, and then back it down to 75, 50, 25, and then 0, and then do impulse tests from 0 to 25, 0 to 25, yes, 0 to 50, 0 to 75%, and then 0 to 100% of the full load capacity. So what they're doing is their intent is to look at, well, what's the impact and what's the response of the facility? You know, they're looking at the real loads on the output, usually of the UPS systems and all the power systems, to make sure they're behaving according to the system design and the manufacturer specifications. So you can see here's the step loading and current for phases A, B, and C. And you can see, just as an example on phase A, I didn't want to crowd this too much. B and C are available, but they're not plotted here. This is the impact on the voltage. And you can see in this example how the voltage is fine. And typically when you get to these impulse tests here, 0 to 50%, you can see it starts getting around the limits, which I believe here are plus or minus 10% of nominal here. Okay, so you can see the impact. So a very important thing is when you're running on generator is what is the impact on frequency. So this is DranView. Those of you who are unfamiliar with DranView, there's tutorials on the website under the webcast page in the support tab that'll give you some of the information on how to navigate DranView. But basically on the left here, what we see, these are events recorded by the power monitor. This is an historical plot of the entire power survey, and the rightmost pane, okay, these are the event details of any events selected over here. So very important to this type of application is looking on what was the impact of the voltage, the current, and the frequency at each one of these step load changes. Now, two advantages to Dranit's products here. We'll talk about some competitive advantages. So Dranit's, the HDPQ family, and specifically the Guide and the Explorer, because they've got very large recording buffers, can have a very large pre and post trigger. And what that means, it can record basically up to 10,000 cycles every time a PQ event happens. And typically in this type of application, the end users will choose maybe 50 or 500, 750 or 1,000 cycles to be recorded at around the time that this event occurs. And that's that impulse, that change in load, okay? So just to let you know, the Guide and the Explorer can do up to 10,000. The Visa is our entry level. It can record only up to 100 cycles in any one of the events. But regardless, this can be recorded by the meter. DranView has the unique capability via its harmonics and time plot calculator. And again, we have application notes and webinars on our website describing in detail what I'm talking about. It can take every one of these waveforms and compute the frequency of it. So what that means for this specific application, at any point in time, I can look at here's what the voltage is done on any phase. Here's what the current is, but most importantly for my generator application, what was the impact on the frequency of the system? So I do all these step changes and impulses, and this is how my frequency changed over that test. And that's critically important for these type of applications. So here you can see everything was kind of fine. You can see this is when the event occurred, which I've already pre-selected here. You can see this is what happens to the current goes up, the voltage goes down. So that means before in our directivity, that means it's a downstream event from where I'm monitoring. And I would suppose maybe they're looking at the utility service entrance at this particular point. That may be combined with the generation. I don't know for sure. But most importantly for this type of application, this is what happens to the frequency. So this is what tells me this is probably looking at a generator at this point, because the utility supply probably wouldn't drift as much on frequency. You could see how the frequency is fine at around 60 hertz, okay, with no load, but when they step in the load, okay, which is that going to 100% here, which is their worst case, you can see how that frequency dips down to actually below 55 hertz here, down to 54 point something hertz. That's critical. I can't judge whether this is pass or fail in this situation. I don't know the requirements for this application, but looking at the power quality, looking at the reduction, the sag, and any swells that have occurred and the effect on the frequency kind of pull this all together on power quality monitoring for a very, very real world application here. Okay, and Ken just brought up a good point that this capability is only available in DranView Enterprise. So when you purchase our PQ packages, if you purchase an HDPQ Visa package, it has a DranView Pro bundled in it. Has many of the features here, but does not have the same feature set as the DranView Enterprise. When you purchase the HDPQ Guide or the HDPQ Explorer or Explorer 400, that comes kitted with DranView Enterprise, which includes this capability, their harmonic and time plot calculator, and a whole bunch of other capabilities. Again, go to our website and go to our webcasts, and you can see them described and demonstrated and training you on how to use them. So however, if you do own DranView Pro and you need these capabilities, just a small cost to upgrade to DranView Enterprise and you can gain these capabilities. So it's not specific to the instrument, it's specific to the version of DranView that you have. So okay, let's just go back to the slide presentation here. We are just about done. And so just as a last thing, if you remember in our last webinar, we focused on energy monitoring. And we, towards the end of that webinar, we compared the energy consumption of an incandescent light bulb to a little bit older compact fluorescent light bulb to a newer LED light bulb. So we left you guys hanging there, if you were on that webinar, asking the question, are there any PQ concerns? So let's just skip to the next slide. Well, the answer is, do you see any PQ problems here? And we'll just kind of set it up. This is the current of the incandescent bulb. This is the current of the compact fluorescent bulb in green, and the blue is the current of the LED bulb. Okay, so are there any PQ concerns? Yes, you can see this is the current that they're drawing, the incandescent bulb. And I'll note that these harmonics on the incandescent bulb didn't come from the bulb. They're probably just in the power system in our lab out not too far from where I'm sitting, where we did these tests. Okay, but you can see what the current draw is on the CF bulb and the LED bulb. And just to give you a little hint, these are harmonic issues that they can potentially cause. So we're going to see the results and kind of break that down a little bit more in our harmonics module, which is our fourth module in our power monitoring seminar series. Again, the next one on July 11th at 11 a.m. Wednesday.